This is the paper submitted in IEEE Latin America transaction. The paper title is Electric Field Redistribution Driven SEGR Mitigation in a High Gate Trench VDMOS with Floating Island. Paper ID is 10555. Problem statement and conventional device. In single event gate rupture, the transient field across the gate oxide exceeds the critical dielectric strength of the oxide, which cause catastrophic failure of the device when operating in radiation environment. Proposed VDMOS high K with p-type floating island. In this work, we present a TCAD-based study that investigates the co-integration of a high K silicon dioxide stacked trench dielectric with a p-type floating island embedded in the drift region of a silicon trench VDMOS. This combined structure enables simultaneous dielectric field redistribution at the gate oxide and charge modulation within the drift region, allowing a coupled control of the transient electric field under heavy ion radiation. Figure 3 shows the electric field distribution for conventional and proposed device. Here we can see that with the varying concentration of p-type floating island, we can see that the electric field is drastically reduced in the proposed device at the trench corner and bottom side. Figure 4 shows breakdown voltage and electric field as a function of floating island concentration, where we see that at 2 e to the power 16 doping concentration we have maximum breakdown voltage of 242 volt. Figure 5 shows breakdown voltage and electric field with varying position of the PFI in the drift so that we can have maximum interaction wherein we can reduce the electric field at the trench bottom. Figure 6 shows specific horn resistance with respect to the conduction section remaining after insertion of PFI of different length in the drift region. Key IA radiation result. The result shows that the conventional device could not sustain the electric field at the bottom undergoing gate rupture at an LET of 20 MeV cm square per mg and VGS equal to 0 volt. For LET 20 and VGS 0 and minus 10 volt, we can see that the maximum electric field across the oxide is increased from 8.5 megavolt per centimeter to 10 megavolt per centimeter at VDS equals to 100 volt rise when VGS is changed from 0 volt to minus 10 volt. 0 and minus 10 volt in figure 9a and b, we can see that the maximum electric field across the oxide is increased from 7.5 to 8.5 megavolt per centimeter for an VDS of 80 volt rise when VGS is changed from 0 to minus 10 volt. The maximum electric field across the oxide is increased from 7.5 to 8 megavolt per centimeter at VDS 80 volt and VGS from 0 to minus 10 volt. Conclusion. Under heavy ion radiation, the proposed device help in delaying the onset of gate rupture. Here we can see that the device sustained operation up to LET of 40 mega electron volt centimeter square per mg, which shows that it can be sustained up to 35% of the rated breakdown voltage. The coupled dielectric and drift field region engineering helps in mitigating single event gate rupture. Thus, the design provides physics-based guidance for developing radiation-tolerant silicon power MOSFET without sacrificing electrical performance. Thank you.